future in your hands, baby. I'm yours, I'm gonna be yours, and here I am, baby. Yeah, I'm yours, yes, I'm a future in your hands, baby. I'm yours, I'm gonna be yours, and here I am, baby. Yeah, I'm yours, yes, I'm a future in your hands, baby. I'm yours, I'm gonna be yours, and here I am, baby. I'm yours, yes, I'm a future in your hands, baby. I'm yours. One, two, three, four. Like a fool, I waited sick too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. That time I waited, said goodbye. Yeah, baby, I won't back and not ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Baby, I'm yours. You got my future in your hands, baby. I'm yours. I'm gonna be yours, and here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours. I'm gonna be yours, and here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours. I'm gonna be yours, and here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours. One, two, three, four. Like a fool, I waited sick too long. Yeah, baby, one more night, your love's still strong. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. That time I waited, said goodbye. Yeah, baby, I won't back and not ashamed to cry. Ooh, baby, here I am, signed, sealed, delivered. I'm yours. Baby, I'm yours. You got my future in your hands, baby. I'm yours. I'm gonna be yours, and here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours. I'm gonna be yours, and here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours. I'm gonna be yours, and here I am, baby. I'm yours. Yes, you got my future in your hands, baby. I'm yours.
How's it going, everybody? Welcome, welcome, welcome. It's Friday. It's May 1st. It's 10 days until the AP exam. And we are here to do some physics. We're here to do some physics today. So it is, like I said, 10 days to the exam. So a couple things we're going to do today. We are going to get some critical updates for the AP exam. And go over some materials that were distributed. And I apologize if this is a review from your other AP classes, but it's good information to have regardless. We'll go over the rotation FRQ as well as some MCQs that I pulled out as being the most difficult of them all. And then just a preview of next week. We're going to be doing our last exam prep, which means we'll be doing, this week we're doing Unit 3 and 4. We'll be doing Units 2 and 1. And also making our note sheet. So we'll probably announce a little bit of a special stream schedule for just the last week before AP exams. I think I'm going to try to stream a little bit more often for that. All right. Well, we're back into mechanics after a long stint in E&M. So here we are. So let's talk quickly about the tasks for this week. So basically this week, this is a little strange because we're getting back into materials where we had done more of the progress checks. So our goals for this week are to complete both the Unit 3 and Unit 4 progress check FRQs. I will eventually get around to doing and scoring all of those. So that just takes a little bit of time that I need to sit down and do. If you had not completed your MCQs for this when we did them in the fall, I've reopened them so you can go back and fix your answers or complete your FRQs or complete your MCQs or whatever you need to do by way of review. Notice the official AP live stream is I think doing practice FRQs. They're doing all sorts of interesting stuff, so you should be checking out their videos. If you can't watch the live streams, you can always check out the VODs later posted on YouTube. I can put up a link, or you know where to find it. So always good things to look at because they're the best arbiters of what is really the thing. So next week we'll announce a little bit of a different streaming schedule. I think I'll also be streaming on Wednesday for AP Physics at least. So just for preparation. There are some new links posted on my MCPS that I think you should check out, and I will highlight them more over time. Which are three things: an AP testing guide, which we'll look at right now, an AP exam checklist, and then there's a demo link. So I want to talk about these in kind of opposite order. The demo link takes you to a website where you can put in a code. Right now, because you don't actually have your e-ticket code, if you type in the code practice, it will take you to a practice exam. It's not subject specific. By a practice exam, what I mean is that if you type that in, it will give you a timed simulation of your AP exam. So it'll have a timer. Once you click go, it'll give you a 5-minute setup timer, and then it will present you with the timed questions. And it's a really good way to practice your setup to make sure that you know how you're going to do your work, take a picture of it, upload it. Or do your work in a Google Doc and attach it, or do your work in a Word doc or whatever and attach it. I would just make sure that you do that demo link at least once, if not multiple times, to just check your setup. Because again, you will have a 5-minute window after the completion of a question to submit your answer. So the practice demo link is really, 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 really valuable. And that will actually be another thing on our task list for next week. I wanted to look quickly at the exam checklist is a printable document, which is linked there. And I don't want to spend too much time going through it. But the idea is it's like what it says. It's a printable checklist to make sure you've done all the things you need to do for your exam. The testing guide is also posted. And this is something that I want to look at a little bit more closely. With you. So the AP testing guide is this long 51-page document PDF. We're not going to go through all 51 pages right now, but I wanted to kind of step through a little bit of it with you. It's got a whole bunch of summary of resources as well as links. Exam day checklist, again, that testing demo that I talked about. It says available May 4th. It's available right now at that link, and things like that. Required documents that you should print or download for specific exams, and things like that. What's in this guide, how to get your AP exam e-ticket and what it is, steps to take before exam day and everything like that, as well as things on exam day and stuff for scores and afterwards. There's just some really good information here about your e-ticket. You should get it by email 2 days before the exam. If you don't get it 2 days before the exam, so that's May 9th for us. If you don't get it, you should, contact Miss Salvato or myself or somebody right away. Probably Miss Salvato, but if she's not responding, you can get to me first. And so, just a second, sorry. Yeah, this is your e-ticket. That lets you into the exam. Oh, woo, okay. Oh, come on, people. Why is this so incredibly sensitive? All right, so again, our exams are on the 11th at noon and at 2 p.m. Don't miss those times. If you oversleep, you will miss the exam. So don't do that. It is worth noting, although the exam is at noon, you should log in 30 minutes. You are entitled to log in up to 30 minutes, and you should do so before the exam. Don't log in at noon, because the site will be busy, the site will be slow. If your internet cuts, don't put yourself in that position. Log on at the right time, which is half an hour early. There are June makeup dates. If you have a disruption, so if something bad happens with your exam, you don't, with your internet or with whatever, contact Ms. Salvato, and we'll deal with it. Exam schedule. Exams will be taken simultaneously worldwide. That's fascinating, of course, if you're in the middle of the night or something. Yeah. Again, it's not going to be harder this year. It's just going to be different. And everything like that. This is a really good document to read through. If you don't pass, if you don't get a score of 3 of a higher, and you really think that if you had the multiple choice section you would have, you can request a review and confirm your score. So if you're interested in that, you can do that. There's 3 different options for submission. You can copy and paste a type response. You cannot type directly into the form, by the way. You need to type somewhere else and then copy and paste it. I tested that today. You can attach a document, which is a pre-typed response, or attach 1 or more photos of a handwritten response. If it's a handwritten response, make sure it is really legible. You know who you are. If your handwriting is terrible, maybe you should type it and only use handwritten stuff for absolutely critical, like drawing a free body diagram or whatever. They've got some more details about how this is doing it. By the way, they will only accept Chrome, Firefox, Safari, or Microsoft Edge for that. There's a couple of very important things. Type your AP and initials, AP ID and initials at the top of the response. So if you're submitting a document, if you're copying and pasting a response, make sure your AP ID and initials are on it so that they know it's yours. Again, these are subtle things. Make sure you do them. Don't include images. Save your work often. Attach a document. So again, read through these carefully. Don't include images. AP ID and initials, same. It won't let you submit until the timer has 5 minutes remaining, I guess to prevent people from, putting things together early. Similarly, with option 3, work out now what you're going to do. Option 1, 2, or 3, work out now what you're going to do, and then practice it on the practice demo test site. Practice it a couple times. Make sure you're really polished at it, because you don't want to run afoul of that 5-minute warning. If you're taking the music theory exam or world language exams, there's some special things in there, accommodations as well. You can request makeup exams. There's a bunch of steps here. Make sure that your contact information is correct. Practice submitting your response. Check your technology. Know what your setup is. Communicate to your parents or your other siblings, right? Like when you need the computer. If you've got other siblings who are taking AP Calculus at the same time, like figure out how you're going to make that work. And if you've got big problems, contact Ms. Salvato and she can try to help you. So I would read through this carefully. This is a weird scenario. You're not just going to walk in and they're going to hand you a pencil and a packet. There's a lot more on you to get set up here. And if you think that's going to be a problem, what you need on exam day, yeah. So class notes, study guides, things like that. So, be cautious. You should, by the way, have for physics a calculator and your formula sheet. So I'll post up links to those if you can't already find them and print them. But you should have your equation sheets as well. So some things here, right? You can use class resources and class notes on this year's AP exams. So shared study notes must be downloaded to your device. So they're not going to let you be looking at Google Docs at the same time that you are working. But we're going to put together some Google Docs next week so you can print it out and have it at your side. Internet searches will waste your time and put you at risk of an exam violation. Don't Google around. It's just a trap. It's just a trap. And chances are if you Google around and find something, somebody else is going to find some same thing. And the College Board is really good at figuring out, oh, these 10 students all submitted very, very similar responses. Better Google that and see what comes up. Don't do that. So we can use our class notes, but that's different. Look for your confirmations and everything like that. There's a checklist for exam day, 30 minutes beforehand. Check in, log in, and then you can just sit and watch a timer for half an hour. We are on the 2-question exam, so we'll have a 25-minute question, 5-minute response window. 15-minute question, 5-minute response window. We're not, lots of good advice here. Exam security, checking into your exam, you'll see something like this, time until exam starts. Once the exam starts, the first exam question will appear. Don't refresh your browser, answering exam questions, etc., etc. Read through this carefully. If your browser closes or whatever, you can click your exam e-ticket to get back to the exam. Some information on scores, July 15th again. Colleges are still on board. So read through this carefully. And if you have questions, let me know. All right. With that in mind, again, key points, check in 30 minutes early, practice with the demo link, know your setup. All right, with that in mind, let's talk a little bit about rotation and do this FRQ, shall we? So some keynotes here, things to remember for rotation. Remember, V equals R omega is one of the most important things, right? This is our rolling without slipping condition. This is how you get back and forth between linear velocities and rotational velocities. And similarly for acceleration, A equals R alpha. So these are really key. For calculating moment of inertia, we've got, remember for point masses, you add up all the MR squareds, whereas for continuous objects, you have to do an integral. Usually, for an object like this, like if you have a stick, right? Usually that dm turns into if you've got a stick of constant density, right? We did a lot of these m over L dx, right? And then your integral turns into x squared m over L dx. Sometimes for spheres and stuff, it'll turn out to be different. But usually it's density times dx or density times dr. Basically, dm, you've got to end up with a density in there somewhere. Sometimes they'll give you a density function and you need that. For doing conservation of energy for rotation, you need both linear and rotational, unless for some reason it's not doing one or the other, right? If it's fixed to an axle and it's not moving, only spinning, then you only need 1/2 I omega squared. If it's a block that's just sliding, you only need 1/2 mv squared. But for things that are rolling, you need to do both. Typically, for things that are experiencing both forces and torques, and we'll see this on the FRQ, you need to consider both F equals ma and torque equals I alpha. And note, obviously, that you need to pick an axis to consider torques. You also will need to consider your I based on where you choose your axis. Remember the parallel axis theorem, which is that if you shift your axis a distance d away from the center of mass, your I becomes, so here's your center of mass, and I move my axis a distance d. My new I is the old I plus md squared. Last but certainly not least, actually not last at all, to calculate torques, it is a vector cross product, but in our class we usually do it as RF sine theta. Notice the theta is between the r vector and the force vector, the radius and the force. That may not always be the angle that you're given in the question. Sometimes you have to consider sine or cosine. The best way to do this is to remember that it's the perpendicular component of the force, that torques care about how much the force and the radius are perpendicular. More perpendicular gets you a bigger torque. More parallel gets you a lesser torque. Last but not least, angular momentum. Remember that L equals I omega, although for a point mass, like a ball, it's just mv times r times the perpendicular radius of its path. And that if there's no outside torques, angular momentum is conserved. All right. Also, the directionality of these things, the right-hand rule, right? If something's spinning this way, omega is points straight up. All right, let's get into our FRQ then. This is a fairly classic rotation question. So you have a 250-gram snowball, so I'm just going to make a note that that's really 0.25 kilograms. Of radius 4 centimeters. So some unit conversions here. Starts from the top of a peak and rolls down a section angled at 30 degrees to the horizontal, and it reaches a flat section of roof 2 meters lower than the peak, and is partially covered in snow as shown above. Okay. On the dot below, which represents the snowball, draw and label the forces, not components, that act on the snowball. And in this case, because we're doing rotation, we want to do them where they start. So in this case, we've got 3 forces. We have gravity, which starts at the center of mass and goes straight down. We've got the normal force, whose point of contact is here and goes up perfectly perpendicular, Fn. And then, of course, we also have friction. And the challenging thing about friction is which way does it point? Well, notice that our snowball is going to start to rotate this way. And the reason it's going to rotate that way is because of friction. So friction's gotta kind of help it do that. You could also think about it wanting to slide down and friction opposing that. But in this case, friction is going to point uphill, directly, perfectly parallel. Uphill. And if it does roll without slipping, it is static friction. Part B then asks, which of the forces produces any torque on the snowball as it rolls around its center? So again, let's just denote the center here. Notice that Fn and mg provide no torque. And the reason they provide no torque is they both are directed exactly through the center. They are radial. So they are parallel to the radius, which means they provide no torque. So only static friction provides torque. Only static friction provides torque. All right. For the points breakdown, these first two, part A was 3 points, 1 for each vector on your diagram for correctly drawing and labeling. So if they ask you to draw a free body diagram, make sure to draw it clearly and label it. Mg, N, and frictional force pointing uphill, 3 points, 1 for each vector. Part B is 2 points. 1 point for indicating that friction is the one that provides torque. And then the second point is for arguing why it provides torque, which is specifically, it's the only one that doesn't go through the center. That the line along which the force is applied matters. So 2 points for that. Then we want to calculate some things. We want to calculate the linear acceleration of the snowball as it rolls down the inclined section of the roof. Well, there's a couple different ways to do this, but the most fundamental one is we've got to use we've got to use, what am I going to say? Newton's third law. Let me just paste this in here. And specifically, we have to use, Newton's second law. So specifically, we've got to use it 2 times. We're going to have to run F equals ma. We're also going to have to run torque equals I alpha. So let's run F equals ma first. Noting that in the parallel direction, which is really the only direction we care about, we have 2 forces. We have the parallel component of gravity, mg sine theta. That's a really good one, by the way, to have on your note sheet. Which one's mg sine theta and which one's mg cosine theta. Minus the static friction force. Please don't put mu cosine theta here. And the reason I don't want you to put mu cosine theta here is, remember, static friction can be anything up to mu times the normal force. But we don't actually know what friction is here. So we've got that. We also need to do a little torque equals I alpha action. And remember, we just said the only one that provides torque here is going to be this. So this will be Fs times R, where the thing's got a radius R. Now, the one thing that they don't give you here is they don't give you the I for a sphere. So in this case, it is 2/5 mr squared. So having a little table of those would be helpful. I times alpha. So you'll notice we got some r's on each side, and we can go ahead and cancel one of them. And then the other r is just hanging out, but here we have r times alpha, which conveniently, if we remember a equals r alpha, this is our acceleration. So what we find from looking at torque equals I alpha is that our static friction force is 2/5 ma. So we can go ahead here and now plug this back into over here. So we get mg sine theta equals, so if I add fs to the other side, I get 2/5 plus 1, or 7/5 ma. My masses go away, which is kind of convenient. And I find that my acceleration down the ramp is just equal to 5/7 g sine theta. And this is where I can go ahead and grab my calculator and do 5/7 times the sine of, make sure I'm in degrees. Here you are free to use 9.8 or 10. I'm going to use 10 just because usually you're allowed to use 10. And I get 3.57 meters per second squared. Note, if you use 9.8, that's also fine. So here you had to use both. You had to use F equals ma and torque equals I alpha in order to make life better. All right. Then we get to use conservation of energy, calculate the angular speed of the snowball as it reaches the end of the inclined section of roof. Well, again, this is going to be conservation of energy, so we'll use mgh. Starts off with a certain amount of that, turns into 1/2 mv squared plus 1/2 I omega squared. So we can go ahead and do some substitutions. In here, we want the angular speed. We want omega. So I'm going to get rid of v and replace it with v equals r omega. So r squared omega squared plus 1/2. And again, I know my I is 2/5 mr squared omega squared. So a couple things that I can do right away. I've got an m everywhere, so by m's. I also have a 1/2 and a 2/5, so that becomes a 1/5. So what I get is let me just rewrite my whole equation here. On the left, I just have GH left. And on the right, I have 1/2 plus 1/5 r squared omega squared. So I happen to know, looking at my calculator, 1/2 plus 1/5 yields me 7/10. So I can rewrite this as 7/10 r squared omega squared. Or come here and write omega squared equals 10 gh over 7r squared. Or just, square root that whole buddy. So omega is going to equal root 10 gh. 10 times g times height here is 2 meters, divided by 7 times r squared. It's 4 centimeters if I recall correctly. It is 4 centimeters. Go 4 squared. And I get 133.6. My units are, of course, radians per second. And that's my omega. So again, what did we have to do here? We had to do all of that good stuff. Yeah, if you got 132, remember, if you used 9.8, that's fine. And again, if your calculations are slightly off, you round it or whatever, they usually don't take points off for rounding if they can see that you're in the right ballpark because, oh, you did the right thing, but you rounded off. Like, don't, if you got 132, if you got like something a little higher because you like rounded something off halfway through a calculation, like no biggie. All right, so let's just look at the scoring for C and D real quick. C is actually the most valuable question on here, calculating the linear acceleration. That's 5 points. 2 of those points are for using F equals ma and torque equals I alpha. Right? There's a point for relating the friction to the acceleration, so doing your F equals ma properly. And things like that. And then basically the last 3 points for solving it. D is worth 3 points. A point for using conservation of energy that includes both linear and rotational kinetic energy. A point for correct substitution of 2/5 mr squared. And again, usually they give you that. I'm a little surprised that they didn't. And a point for correct substitution of V equals R omega into that equation. So for part E, let's just quickly look at it. A second snowball with the same radius that's packed so it is more dense than the original rolls down the same roof. So I just want to stop and say, if it's more dense with the same radius, more dense, same R, that means that the mass has increased. Will the angular speed at the end of the incline for the new snowball be greater than, less than, or equal to the original snowball? Well, if you look at your equation, and this is one of the great strengths of doing things symbolically until the very end, mass, so radius appears in this equation, but the radius is the same. Mass doesn't appear anywhere in this equation. So this equation is insensitive to mass. So in fact, it just stays the same. It just stays the same. And this was a 2-point question. 1 for selecting stays the same, and 1 point for pointing out that your equation doesn't include mass at all. You do have to justify, so if you did what I did here and just clicked stay the same, you do have to write out a justification, right? You can say, like, mass doesn't appear in the equation, therefore, et cetera, et cetera, et cetera. Give, please, full responses, especially on this exam where there's a lot of writing and not very much calculation. All right, and that is the whole FRQ. Not too bad. I thought it was a pretty classic little rotation question. All right. So there were a couple of these MCQs that I wanted to go over quickly in the next 15 minutes. These are the ones that I picked out, by the way, where more than half the class did not get them correct. So you can see for this one, right, the plurality got question 1 correct, but more students got it wrong. So the students run an experiment. Okay, I don't like this question, but I still want to go over it. The rotational inertia of an object. They determine a weird thing. They determine that the radius is a function of the mass, which is a little strange. So we get R equals km squared. So as I increase the mass, the radius increases with k equals 3. what they want you to do here is be like, oh, this is r squared dm. So why don't I just go ahead and plug that in? K squared m to the fourth dm. It's kind of silly. So we get k squared over 5, m to the fifth. And I guess we're integrating here. Nope, that's k squared. Yeah, and that's fine. So you get 9 over 5. And 9 over 5 is, of course, 1.8. So that one's kind of silly. This is, it's just kind of silly. All right, blank one. Question 3. We have 2 identical spheres of mass m that are fastened this way. And then you get a bug that sits on one of them. And then it's going to start to rotate, right? At first it would be stable, and then when the bug lands on it, it's going to swing around. What's going to happen? Well, a lot of people checked that angular momentum would stay the same. I just want to point out, angular momentum only is conserved if there's no external torques. The bug landing on this thing generates an external torque. There's, a big old gravity thing down here, a big torque on it. So L does increase. What happens to the gravitational potential energy? Well, the bug gets lowered down. So the gravitational potential energy actually decreases. And the other way to realize that the gravitational potential energy decreases is that what happens to the kinetic energy? The kinetic energy increases. So L is going to increase, potential energy will decrease for that one. For 5, angular kinematics, constant acceleration. A disk begins rotating from rest, so omega 0 is 0. Angular acceleration of alpha, and the time it takes in seconds for the disk to complete one full rotation, so delta theta is 2 pi, and we're looking for time. Well, in this case, I can use my distance equation, right? I can use delta theta equals, omega 0 t plus 1/2 alpha t squared. Now notice, of course, that omega 0 is nothing, so I just end up with 1/2 alpha t squared. So now I can just plug in, right? I just get 2 pi equals 1/2 alpha t squared, or t squared is root 4 pi over alpha. Many people wanted to say d, and I think you get d, and you're just like, oh look, it's so tempting. There's a 2 pi. The 2 pi is right there. Do the equation. Be careful. Don't get snagged by that. Don't get seduced by the little 2 pi. Again, some calculus-y kinematics. Rotational inertia is 10, I guess. It's got an angular velocity of this. Actually, I guess it's kind of the angular rotational inertia is not important. Angular velocity is given by 2t cubed minus 4. So what's the displacement? Well, we're just going to integrate this from 1 to 3. Remember, displacement is the integral of velocity. So we can just integrate 2t cubed minus 4 dt from 1 to 3. World's longest equal sign. So that gives us, what, 1/2 t to the 4th minus 4t from 1 to 3. So I could also just use my calculator for this. So this is 81 over 2 minus 12 minus, plug in 1/2 minus 4. So I get 80 over 2, which is 40. 40 minus 12 is 28. Plus 4 is 32. So just do your integral cautiously. Number 11, a torque versus time graph. I would expect to see a lot of questions like this. Obviously, this is multiple choice. But expect to see a lot of graphing questions. Just that's what I would do if I were them. It's applying torque, and we've got a graph of torque versus time. That looks like a straight line with positive slope. What aspect of the graph could be used to calculate how much the disk's angular speed increases during the process? Well, let's just remind ourselves, right, of torque equals I alpha, right? Taking the slope here, right, is kind of like taking the derivative, which is going to give us like I times, I guess, the derivative of acceleration, I guess rotational jerk. Not that helpful. If I take an integral instead, though, well, what's the integral of acceleration? The integral of acceleration is change in velocity. So it's kind of like integrating force over time, right? If I take an integral of tau dt, it's like rotational impulse. I get I times the integral of acceleration, which is delta omega. So then I have to divide by the rotational inertia. I have to divide by the rotational inertia. So you got to add up those forces over time. All right. Again, another graphing question. In an experiment, a varying force is applied tangentially for a period of time to a solid disk. Initially, the disk is at rest. What type of graph should be created so that the final kinetic energy of the disk is represented by the area under the graph? In this case, I didn't look at the answers, but presumably we want to do torque versus time. If we just do force versus time, we're not going to get, it's not actually moving. We're not going to get the right thing. So we actually want to do torque versus time. Let me see if that's one of the valid answers here. It should be. Bloop, 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 bloop. Question 14. It should be one of the valid answers. Oh my gosh, my computer's freaking out. That's okay. We'll get through the last couple of these and we'll close down for the day. Next week's going to be a big week. Okay, well, it's being very slow to load. I don't want to take up your time with that, so I'll send out a message on Remind if I'm wrong about that. It should be torque versus time. In the same way that the integral of force versus time. Oh, no, I'm wrong. I'm very wrong. It's not force versus time. It should be torque versus displacement. Because if we think about the linear thing, force versus time, the integral of force versus time is change in momentum. It's the integral of f dx, which gives you work or change in kinetic energy. So here I've got to do my, torque versus angle. All right. A couple more. We've got a puck striking a rod, and it's asking under what circumstances will the angular momentum not be conserved? Well, it turns out that the answer here is it'll always be conserved. The only way that it would not be conserved is if there is so L is conserved as long as there's no external torque. So there's nothing else in the system except the puck and the rod. Angular momentum will always, always, always be conserved. If there were friction or something else, that would be different. Note that linear momentum is not conserved here because there is presumably a firm axle keeping this rod from moving. Last but not, got a couple more, two more. Here we've got these two little discs connected by a belt. The belt speeds them up with some torque. From an omega 0 to an omega final. What's the change in angular momentum? Well, please note, right, that, it's going to be L equals I omega, right? So any change in L is due to that. What's our delta omega? Well, it's going to be, final minus initial. Where a lot of people got tripped up is how many disks do we have? We have 2 disks. 2 disks makes for double the change. Last but not least, we have a solid disk of mass m and radius r that's rotating around a central axle, and a thin ring also of mass m and radius r, but that is not rotating, is dropped on the solid disk, and they come to a final common speed. This is a conservation of angular momentum problem. Our initial angular momentum is all in the solid disk, which is to say the solid disk is going to be 1/2 mr squared omega. Our L final will be the two of them stuck together, so it'll be 1/2 mr squared plus, for a ring, it's just mr squared times omega final. Note, this is conservation of momentum and not conservation of kinetic energy. It's an inelastic collision. So we can set those two equal to each other. 1/2 mr squared omega equals 1/2. Well, I guess I can do, in this case, this should be 3/2, right? 1/2 plus 1 mr squared omega final. Notice that we get a nice thing. Our mr squareds go away. We can even take out a 1/2. And what we find is omega equals 3 omega final, or omega final, to put it a better way, is 1/3 of omega. We cut our angular speed to 1/3 of what it was before. So if it used to be 2, well, 2/3 is the correct answer. So there you go. Hopefully, I guess all the answers are slower. So, but in this case, it's a lot slower because the eye of the ring is much, much bigger. All right, that's going to do it for today. Next week, what we'll be doing is we'll be doing the unit 1 and 2 and 3 and 4. We'll be going over the 3 and 4 and doing the unit 1 and 2 FRQs. So we'll be streaming twice next week, and I'll send out messages about that. We'll be creating our notes sheet as a shared Google Doc for the class, so we can put lots of good information in there. Critical equations, notable concepts, notable graphs. So this is like, what graphs do we want, right? So, you know, if you have like f versus x, that, you know, what does the slope give you? What does the area give you? Things like that. Key concepts, and maybe, no memes in there. We want to keep this tight. So, all right. In any case, I'm going to sign off for today. I will be back up at 3 o'clock with aerospace, but otherwise have a wonderful weekend. We are 10 days out, so make sure that you are getting those FRQs done. I'll get grades updated as soon as possible. Ta-ta.